Well, when I was an undergraduate, I declared chemistry very early as an undergraduate. But essentially I liked everything as an undergraduate. I liked math. I liked all my science courses. I liked history. I liked English. But I was aware of the need to find something where I could find a job. And I thought chemistry would be an area that's very versatile and very open, so I could probably find a job in chemistry, although I liked everything. I just wound up taking more chemistry classes, and that's what I graduated in. Because of the rise of biological chemistry, I do wish I'd taken more biology courses. I liked math and I liked physics, so I tended to focus on that sort of more physical side of chemistry. And I, at the time, didn't really like biology. I didn't see a whole lot of need for biology. But my big regret is that I didn't take more biology courses, because biology has changed very fast. And it's a little hard to go back and learn what I didn't take at the time. So yes, I would take more biology. Well, I think some abilities you just have to have in the sciences regardless, and that would be logic, reasoning ability. I think those would be selected very early in your career. I think some softer skills that people don't really realize is really the ability to work with other people and to communicate well. It's pretty rare that scientists work alone. Scientists are always working in teams. They always have to write as a group. They have to communicate as a group. So those skills that I think, again, communication and working with people aren't often seen as certainly scientific skills necessarily, but they are hugely important in doing well in your career as a scientist. Today I'd like to discuss with you the behavior of gases, how this behavior can be used in chemistry calculation. As you know, matter can be thought of as either a solid, liquid, or gas. Gases, however, have been studied very extensively, simply because prediction of gases can be made quite accurately. Gas behavior can be made quite accurately, simply knowing a few variables about the gas. And these variables are the amount of gas, the amount we're talking about the moles in for that, pressure, capital P for that variable, volume of the gas, capital V for that variable, and temperature of the gas, capital T for that variable. These four variables are. The relationship is known, so just using these four variables, pressure, volume, moles, temperature, this is the relationship between those variables. That quotient, you see that if the quotient always is constant, if the pressure increases, then the volume must decrease in order to keep the quotient constant. That would be known as an inverse relationship. Other relationships you can also see between any of these four variables. For example, if the pressure and the amount were constant, if the temperature were to increase, then the volume would also have to increase. This constant has actually been measured. The value for that 0.0821 liter atmosphere. What I'm going to use now, instead of just calling it constant, I'm going to use a letter for that constant. And that letter is going to be R. So using the letter R to stand for the universal gas constant, I can set up the relationship again. My four variables now equal R. I'm going to rearrange slightly. We're going to cross multiply here. Cross multiply here. Slight rearrangement in R. So now I have a linear equation. This is the most common form of what's known as the ideal gas law. The reason the ideal gas law is referred to as ideal is because it can reasonably accurately predict the behavior of all gases, regardless of identity. So, for example, if we're talking about dioxide gas, nitrogen gas, ammonia gas, while the ideal gas law is not perfect in behaving the behavior of each of these gases, it's reasonably accurate and can be used for any gas. Generally speaking, the ideal gas law can be used with one of three particular situations. One situation is simply given three variables, solve for the fourth. Again, remember our four variables: pressure, volume, moles, temperature. Given any three of those, simply solve for the fourth one. Change one particular variable. See the effect on another. And then lastly, use the ideal gas law with the chemical reaction. All right, let's do some examples of each of those. Suppose you have a gas cylinder. This gas cylinder contains 91.3 grams of oxygen. The volume of the cylinder is 8.58 liters. What's the pressure of the gas at 22 degrees C? Well, this is an example of the first situation where you're given three of the four variables, and you're asked to solve for the fourth. So in this case, we are looking for gas pressure. So we're looking for the pressure. The moles of the gas, I said that we were given the moles of the gas, but we're actually given the grams of the gas. So we have to convert the grams to moles. Molar mass of oxygen. Works up to 2.85 moles. And then we have the moles that we can put there. We always know the universal gas constant. In my class of testing quizzes, I always give that to students. You don't have to, in my class, you don't memorize that. The temperature, we have the temperature. But in the ideal gas law, in most formulas, you have a capital T. Capital T always refers to Kelvin temperature. We have to change 22 degrees C to Kelvin. And the volume is directly given, so then we can simply solve for the pressure. So solving for the pressure, just plug and chug now. Those moles we calculated earlier, 25 moles. Universal gas constant, 0.021 liter atmospheres. Okay. And the temperature we calculated is 295 K. And the volume was given in the problem, 8.5 liters. Universal gas constant units give you a clue as to what the units must be of all the other variables. As you have liter atmospheres, volume is always going to have to be liters. You have moles, so you have to use proper moles. Again, K, Kelvin, you have Kelvin here. Liters will cancel, moles will cancel, Kelvin will cancel, and the answer will be left in atmospheres. case, pressure works out to be 2.04 atmospheres. This is the simplest sort of example using the ideal gas law. As I said before, it's really just sort of a plug and chug calculation. Let's work now with so in this particular example, suppose that you had a 3.15 liter sample of neon gas at 21 degrees C and 0.951 atmospheres. What would be the volume of this gas if the pressure was increased to 1.292 atmospheres? So in this particular situation, we have our sample under these conditions, volume, temperature, pressure, and we're changing one particular variable, we're changing the pressure, seeing the effect on the volume. So simply by the way this particular problem is stated, changing the pressure, looking at the volume change, the presumption is that the temperature and the amount are going to stay constant. So from earlier, when we initially set up the ideal gas law, always equal to a constant, R. So under my first set of conditions, I could say P1, P1, N1, P1. This is my first set of conditions, and it has to be equal to R. This constant is a constant regardless of the actual conditions. So if I change my condition, I could say P2, N2. Since the constant is always a constant, ignore that and you know that P1 is equal to in this particular example, we're changing the pressure and we want to find the volume. So since we're given the temperature, but there's no change in the temperature, we can simply ignore. What about the moles? We weren't given the moles. But if you weren't given the moles, the presumption is the amount of moles is not changing, so we can simply ignore moles as well. So what we're left with then, P1, P2, and now it becomes a plug and chug. P1, P2, and in this particular problem, we started out with initial pressure, first pressure, 0.951 atmospheres, and the initial volume, 3.15 liters. Second pressure that we changed it to was 1.292. Solving for second volume. Cancel. We're left with 2.32. The new volume. The whole point of this sort of calculation, again, is that using this relationship, you can change one of the variables and solve for a second variable. Or even sometimes if you're changing two variables and you know what the other variables are, solve for any particular combination of variables. You simply have to look through the problem and find out which are the given and which ones are constant. So suppose we have via from ammonia and carbon dioxide follows gas, dioxide gas goes to form via plus water plus volume of to produce 908 grams. So this is basically using the ideal gas law in combination with stoichiometry. So we're trying to find the volume of this reactant, but we're given the mass of this product. Well, we'll convert the mass of this product into moles, and then knowing it's a 1-2 relationship with this reactant, we'll have the moles of this reactant. Then once I have the moles of this reactant, and I know the other variables, all gases are 25C and 1.5 atmospheres, I can then calculate the volume of the ammonia. So simply using 908 grams of urea, calculate the molar mass of urea. That gives me 15.1. Urea. Now then I can simply use the 1-2 molar ratio. Ammonia gas is required. Now I'm ready to use the ideal gas. We then knew that there were 908 grams of urea. We calculated the moles of urea to be 15.1. Therefore, it's a 1-2 molar ratio. So we know that we need 30.1 moles of ammonia. And what we're trying to ask for is what volume of ammonia. But now that I have the moles, and I knew that all the gases were at 25 degrees C and 1.5 atmospheres, I can substitute the moles and the temperature and the pressure solve for the volume. Again, the temperature was given in Celsius. We have to change that to Kelvin. So we'll add 493 liters of ammonia gas is needed in order to produce 908 grams.